Okay, Miss Howard Chemistry, and this is Unit 8, Chemical Reactions and Balancing. And we have several of the Texas essential elements that you guys are going to have to know. C8C, you're going to calculate percent composition and empirical molecular formulas. That hasn't gone away. You're going to use the law of conservation of mass to write and balance equations. You have done a little bit of this before in the IPC class if you took it. C7A, you're going to write formulas and name compounds. That has not changed. So C7A and B, write the formulas, name the compounds. You're going to do this for the rest of the school year. C4A, differentiate between chemical and physical changes and properties. We've talked about this before. We're still going to continue working on this. C8A, define and use the concept of a mole. That means you're going to do some calculations. And then C5B, you're going to use the periodic table to identify and explain the properties of chemical families. That's going to show up again here because their properties and where they are on the periodic table helps to determine whether or not or how they're going to react with something else. Okay, so Roman numeral number 1, conservation of matter and chemical change. Capital letter A, the law of conservation of matter and energy. I put it in parentheses there. A lot of times we can keep them, you hear them separate, the law of conservation of matter or the law of conservation of energy, but we can put them together. And this is it's a law that you guys already know. Matter and energy can neither be created nor destroyed, just change from one form to another. So you're not going to pull atoms out of the air. I mean, you're not going to play God and create your own atoms. The atoms are already here. All we do is we rearrange all these atoms that are presently here. So you rearrange the atoms. You don't create atoms. Okay, the primary change, number 1, the primary change that matter undergoes is in the form of chemical reactions. So when we talk about how the matter is changing, we talk about chemical reactions. Chemical reactions involves one or more substances rearranging the atoms to form new substances. So you haven't, again, created the atoms. You're sticking with the law of conservation of matter, but you're rearranging them so they create something totally new and completely different. You have some examples, and these are just everyday examples that you guys know about. Tarnishing, if you have anything silver and you get that kind of black smudge or stuff on the outside of it, it's tarnishing. You're creating, from silver and oxygen, you're creating silver oxide. Same way with rusting, that orangey powder that's on the outside of the iron or the steel is iron oxide. Digesting, there's a huge amount of chemical reactions that occur during digestion process. And then the other one down there is burning. That's a basic combustion reaction. And you are, again, combining something with oxygen. If you look at the first three, tarnishing, rusting, and the first two and the last one, they all are concerned with combining something with oxygen. All right, Roman numeral number 2. The chemical equation has several parts to it, and you guys should be fairly familiar with it. They're not abnormal or really abstract things for you to look at. The chemical equation uses symbols and formulas to show not just the identities, like what the stuff is, but also the amounts of the substances. Okay? Now it says relative amounts because you're showing something in terms of ratios to each other. So if you have 2H2O plus O2, then you've got 2 of the H2Os to every 1 O2. Now, you also have on the left-hand side, usually the arrow is pointing to the right. On the left-hand side, you have the reactants, things that react together. And on the right-hand side, you have the products, things that are produced. Here we have an equation you guys should recognize. Every single kid in the USA, every single young adult in the USA that's been in the science class has seen this equation. Everyone has. C6H12O6 plus O2 yields CO2 plus H2O. Notice I didn't say the numbers just yet. C6H12O6. You guys know what this is. It's glucose, sugar. You know what O2 is. It's oxygen. So the glucose, the sugar, is the fuel that the human body uses or that mammals use. And we combine it with oxygen. And in the process, we produce energy. And we use that energy to move, to talk, to laugh, to smile, to irritate people. But in the process of creating that energy, we also produce some things that the body gets rid of as waste products. And that's CO2, carbon dioxide, and H2O, water. How much do we produce? You look at the numbers in red and you see those are the ratios. So for every 1 molecule of glucose, we need 6 molecules of oxygen, and we end up producing 6 molecules of carbon dioxide and 6 molecules of water. You guys know that we breathe out carbon dioxide, and if you breathe on your hand, you get some of that waste product of water that we get rid of too. Do we also need water for other things? Well, yeah, we do. But in this particular part of the chemical reaction that talks about one of the reactions going on in the human body, in this case, the water is considered a product and a waste product of that. So where should you know this equation from? Every single time you talk about cells, you talk about cellular respiration, and this is the simplistic equation for cellular respiration. Cellular respiration, we're not talking about taking in oxygen, breathing it out. You know, that's like the big overall respiration of what is the function of your lungs. This is on a cell level. So inside your cell, how do the cells produce energy? This is the equation where they produce the energy. So this is cellular respiration. If we take this equation and turn it around backwards, we have photosynthesis. Because plants need water, they take in carbon dioxide, and in the presence of sunlight, there's their energy that they get. They produce their own food, that's the sugar, and then their waste product is oxygen. So if you know this equation one way, then you know the opposite of that, and that'll be the equation for photosynthesis. Learn this equation if you don't know it already. Okay, capital letter A. How do you know if a chemical reaction has occurred? Well, you look for certain signs. Now, when you look for these signs, you always need to keep a little bit of common sense associated with this. Don't get carried away. So the first thing you look for is some type of heat produced or taken in. So some kind of change in temperature. If you're just using your hand and saying, oh, well, it feels cold or it feels hot, that can be misleading. You need to be careful about that. My hands are usually cold all the time, so whenever I touch something else, it feels hot to me. Whether or not it actually is hot, it feels hot to me because I'm gauging the temperature relative to my own hand temperature. So it's best to use a thermometer. Use the tools that we have access to. So when we say there's heat produced or taken in, heat produced would be an example of a firecracker. You guys have used those cold packs before where you have to push a little button in the center and it turns really cold. Well, you have something in many cases where you have a chemical reaction occurring. Again, you have to keep some practicality there. When you have a light bulb, you guys, if you've ever tried to change a light bulb before, you know that it's hot to the touch but just burned out. You know that there's heat given off. That's not evidence of a chemical reaction. So you have to be, again, practical. When you look at that light bulb, the light bulb, there's a little bitty tiny filament on the inside, the older light bulbs, and they run electricity through that, and they run so much electricity through that really thin wire that it gets white hot, and so hot that it gives off light and heat. So you look for signs of a chemical reaction, but you always have to kind of maybe do a little bit more research, and you need to know what it is you're looking at and talking about. Okay, so we have something that is exothermic. Exo means outside, therm means heat. And this is when we say heat is given off. If you feel it in a lot of cases, it feels hotter, but it's always best, again, to use a tool to gauge the temperature and the changes in the temperature. The opposite of exo is endo, so we also have endothermic. And endothermic means the heat's taken in. It actually ends up feeling colder to the touch, but when you check it with a thermometer, the temperature drops. So always use the tools to figure out what's going on here. Number 2. So number 1, we look for some type of temperature change. Number 2, we look for a light produced. So for example, you guys have played with those glow sticks before where you snap them, kind of bend them, something breaks in the middle, and you get 2 chemicals that react with each other, and you have light given off. Again, the light bulb, there's no chemical reaction there. It's just you're running electricity through a thin, thin, thin wire, and the wire resists the movement of the electricity through it, and it glows red, white hot. So the glow stick is evidence of a chemical reaction. It's light where it's kind of unexpected. 2 chemicals are put together, and then all of a sudden they give off light. Okay, another great one is the formation of a gas. You're looking for bubbles being produced or some new odor that's produced. We typically don't want to smell the chemicals. It's never usually not a good thing if you're smelling some strange new odor when you're working in the chemistry lab. Leave. But bubbles being produced, we look for that. If you put vinegar and baking soda together, you guys have done this before, If you put vinegar and baking soda together, you have a chemical reaction and a gas is given off. And the gas given off should be carbon dioxide gas. However, if you've seen those Mentos when you drop that candy Mentos in the soda, that's not a chemical reaction. How do you know that? You don't just know it offhand. You have to do some research. So you're just learning this process. You look for certain signs, and hopefully there's more than one sign that's going on. Or you know that, oh, hey, I can read this, I can look this up in a book or online, and it can tell me quickly whether or not it's a chemical reaction. Okay, number 4, you look for a precipitate formed. Precipitate is when you put two clear solutions together. One may be colored, maybe not, doesn't matter, but they're clear, you can see through them, so they're solutions. You put two solutions together, and all of a sudden it turns cloudy, and if you let it sit there long enough, this solid gunk will fall down to the bottom, and that's called a precipitate. You've produced a chemical that's no longer soluble in water. It won't dissolve in the little bit of water that you have there. Okay, so the solid produced is a result of the chemical reaction in solution, and then it separates from the solution. And a lot of times what you look for immediately is you almost look for this cloudiness in it. Again, use some common sense. If you take some milk and put it in water, it turns cloudy, doesn't it? Yeah, that's not a chemical reaction. So always be practical. Okay, number 5 is a big one. That's the color change. You always look for a color change in these things too. So you get a hamburger patty, it's nice pretty pink, and you start cooking it and it turns color. That's evidence of a chemical reaction. Typically we don't taste to see if there's evidence of a chemical reaction, but raw meat tastes a lot different from the cooked meat, right? So there's evidence of a chemical change there. So when we look at color change, we can look for sometimes what people call an unexpected color change. Like you put a white solution and you put a yellow solution and it turned pink. That's not expected. Yeah. If you take red food coloring and you put it in clear water, it's going to turn it red. That's not evidence of a chemical reaction. So you have to kind of balance it and think, what's practical here? Always keep that in mind. C4A, differentiate between chemical and physical changes in properties. That's a big thing when you're looking for signs of a chemical reaction. And here endeth the lesson.